All right. Bienvenido a mi clase. Yo quiero 20 estudiantes aquí y yo empazo. Nosotros empezamos. Gracias. Tú utilizas su con mi. Yo utilizo tú con tú. Okay. Nosotros empezamos. We begin. I just had my oral exam in Spanish 1 class, so I'm trying to and then afterwards la maestra was like, okay, I'm just going to put you in Spanish 2. So now I'm taking Spanish 2. I'm taking Spanish 1 as well as Spanish 2 on the VHL Central website. Do you guys use the VHL Central website? It's pretty cool. Okay. Okay, that was just me writing my script for the oral exam. I wasn't going to take it initially, but then I got put in a breakout room with a freshman, and I was like, well, I better, if I wasn't going to do the exam, but then I was paired with someone else, and I didn't want them to like fail because they had no partner, so I just went with it. Yeah. Yo fui conductor. Okay. So what are we going to learn about today? Okay, my brother's texting me and it's coming through my watch, and I need to put it down. Okay. So we are going to continue to learn about forces today. Today we're going to learn about forces, basically diagonal forces. Okay, diagonal forces is the topic of today's lesson. So what if we have a force, for example, that is, 80 newtons, and it makes an angle of 30 degrees with the horizontal, okay? So this is actually equivalent to, so anytime you have a diagonal force, you want to break it up into a vertical force and a horizontal force, okay? And so, for example, this component of the force, we're just going to use the laws of trigonometry. It would be the length of this side of the triangle. So this would be 80 sine of 30, because that's opposite the angle. And then this would be 80 cosine of 30. So if I plug those into the calculator, 80 sine of 30 is going to be 40. So this is a 40 newtons. And 80 cosine of 30 is 69 newtons. Okay, so a force of 80 newtons at an angle of 30 degrees is completely equivalent to a 40 Newton force going vertically combined with a 69 Newton force going to the right. Okay, so this is how it works. So we're just going to do examples for the entire class period. Oh, by the way, the other thing I wanted to say was if you have Newton's second law, net force equals ma, it actually works in both directions, okay? So net force equals ma means that the net force in the x direction is equal to m times a sub x, the x component of the acceleration, and the net force in the y direction is m times a sub y. Okay, so Newton's second law applies vertically and it applies horizontally. Okay, so we're going to see how that works in this example. Okay, so what if we have a box okay, let's say that it is a 3 kilogram box. And go ahead and type it into the live chat if you know what the weight force on a 3 kilogram box would be. And that box has a couple of forces acting on it. It has a 15 Newton force acting at 20 degrees to the horizontal, like that. And then it has a 10 Newton force pulling this way at an angle of 60 degrees. Okay, very good. The weight force is going to be 30 newtons, m times g. Okay, so what we want to know is what is the acceleration of this box? And we're going to say that it's a frictionless floor, so mu equals 0. Okay? So, first thing I'm going to do is I'm going to draw a free body diagram. So a free body diagram is a picture of where we represent the object as a dot, okay? And then we draw an arrow for each force that is acting on the object, okay? So we're going to have a weight force going down, which is mg equals 30 newtons. We're going to have a normal force, which points away from the floor, so that would be upward. Okay. We're going to have this diagonal force, 15 newtons at an angle of 20 degrees. And then we're going to have the 10 Newton force at an angle of 60 degrees. Okay? So what we want to do is we want to take any diagonal force and we want to get rid of those diagonal forces and turn them into a combination of vertical and horizontal forces. Okay? So we're going to use trigonometry just like we did up here. So this would be 15 sine of 20. Which is 5.1 newtons. This would be 15 cosine of 20. So that's about 14 newtons. This is going to be 10 10 cosine of 60, which is going to be 5 newtons. And this is going to be 10 sine of 60, which is about 8.7 newtons. So now what I'm going to do, because this diagram is, getting kind of messy, I'm going to redraw it with these diagonal forces now written as a vertical and a horizontal. So for this diagonal force, I'm going to write it as 5.1 newtons going up, and I'm going to write it as 14 newtons going to the right. And then for this 10 Newton force, I'm going to write it as 8.7 newtons going up, and 5 newtons. Now, notice how this force is going up and to the left, so the horizontal part is to the left. So I have 5 newtons going to the left. And then I have the forces that are already vertical or horizontal. So I have the normal force here, and I have the weight force, mg, going down. Okay, so this redrawing the free body diagram like this makes it very simple because it's easy to tell what the net force is in each direction. Okay, so for example, so we have the net force in the x direction equals m times a sub x. Okay, the x component of the acceleration. The net force in the y direction is m times a sub y. So let's write out what is the net force in the x direction. Well, x is horizontal, so the net force in the x direction is right forces minus left forces. So we have 14 minus 5. Okay, so the net force in the x direction is 14 minus 5, and that equals 3 times a sub x. Okay? Type it into the chat if you know an expression for the net force in the y direction. Okay? While I work through this. So 14 minus 5 is 9. So 9 equals 3a sub x. And then I divide both sides by 3, and I get 3 meters per second squared is the acceleration in the x direction. Okay? Now, what is the acceleration in the y direction? Well, you would need at least 30 newtons of force going upward in order to lift this box. Okay? These two forces combined, even if they were both pointed in the exact same direction, upward, they could only combine to a maximum of 25 newtons. All right? Even if they were both going directly upward. So these two forces are not enough to lift the 3 kilogram box. So this box is not going to lift up into the air, and because of the floor, it's not going to sink into the ground. So it can't go up or down. So the acceleration in the y direction is 0. Okay? Is anyone going to type in the net force in the y direction? I'm going to wait about 10 seconds. So the net force in the y direction would be up forces minus down forces. I'm waiting for anyone. Someone, help. No one wants to help. Okay. So there are 3 up forces. There's 8.7 going up. There's the normal force, which is an unknown, going up. And there's 5.1 newtons going up. So we have 8.7 plus normal force plus 5.1. Those are the up forces. And the down forces are 30 newtons. So minus 30. So if I work this out, I'm going to combine all the ones that are numbers. Okay. So 8.7 plus 5.1 minus 30 is negative 16.2. So I have normal force minus 16.2 equals 0, which says that the normal force is 16.2 newtons. Okay? So that's how this works. So oftentimes what happens is if you have an object that is on a floor or is in contact with something, it is constrained to move. It is constrained to move along that surface. So that means that one of the accelerations is going to be 0. Okay? Let's do another example. Okay? So now we're going to throw friction into the mix. Let's say that we have a stubborn child. Okay, so here's the playground floor. All right, and the child is just laying on the ground. Does not want to leave. Okay, and the parent is dragging the child. Okay. I haven't been physically dragged, but I can remember times when I would go to the playground and my mom would say, "It's time to go," and then I would go run and hide because I didn't want to leave. Okay? Similar situation, only this parent is very aggressive and is going to drag their child. The child has a mass of 20 kilograms. And the force that the parent is exerting is 300 newtons at an angle of 25 degrees above the horizontal. Okay? And we're going to say that the coefficient of kinetic friction between the child and the playground is 0.2. Okay? So the first step, the first step is we want to draw a free body diagram of the forces on this child. Okay? So I'm going to represent the child as a dot. The child has a weight force going downward. That weight force would have size 200 newtons, 20 times g. There's going to be a normal force from the floor going up. There is going to be a 300 Newton diagonal force acting at 25 degrees. And then there's going to be kinetic friction. This 300 newtons is going to be enough to drag the child. We'll assume that it's enough to drag the child, so we'll have kinetic friction going to the left. okay? We have to be a little bit careful here. Could 300 newtons actually lift the child off the playground floor? Yes, it could, okay? Because 300 is greater than 200. But if we look at the angle of it, this 300 Newton force is angled basically almost horizontally. And so what that's going to do is it's going to make it so that the vertical component of the 300 Newton force is not greater than 200. So it won't actually lift the child off the ground. Okay? So let's do the trigonometry on this diagonal force. We have 300 times cosine of 25 is going to be the horizontal part, which is 272 newtons. And then 300 times sine of 25 is going to be the vertical component, 127 newtons. So now what I want to do is I want to redraw my free body diagram, okay? But with this diagonal force replaced by a vertical force and a horizontal force. So redrawing the free body diagram. I have friction going to the left, kinetic friction. I have normal force going up. I have 200 newtons going down. That's the weight force. And then I have the 300 Newton force, which can be thought of as 127 newtons going up and 272 newtons, my bad, going to the side. Okay? So that is a free body diagram that is all set up for us to do computations. So who could tell me, who can type it into the chat, what is the net force in the y direction? So it's going to be up forces minus down forces. Okay? So the net force in the y direction is m times the acceleration in the y direction. All right? Now, if we look at the upward force here, it's only 127 newtons. It's not greater than 200. So the child is not going to get lifted off the ground. They're going to get dragged across the ground. So that means that the y component of the acceleration is 0 because the child is not being lifted off the ground. Okay? So whatever the net force in the y direction is, it has to equal 0. Okay? So who can tell me up forces minus down forces? Please. Okay, so 73, you're almost right. So you got to worry about the normal force. So up forces would be normal force and 127. Downward forces are 200. So you guys are not putting you guys are only putting 2 of the forces in. You got to put all 3. So one of the forces is just a variable. So we have normal force minus 73 equals 0, which says that the normal force is 73 newtons in this case. Okay? So the normal force is 73 newtons. Now, what the normal force allows us to do is it allows us to calculate friction. So we learned a formula for friction in the last lesson, which is kinetic friction is coefficient of kinetic friction times normal. Okay? So that means the coefficient of kinetic friction is 0.2. And the normal force, I just found out, is 73. So that means that the kinetic friction is, what, 14.6 newtons. So kinetic friction is going to be 14.6 newtons. So this is 14.6 newtons. All right? So now we go over to the net force in the x direction. Who can type in what is the net force in the x direction? Who can tell me what is the net force in the x direction? That would be rightward forces minus leftward forces. I will wait. How do I say to wait in Spanish? I'm going to look this up while I'm waiting for you guys to answer. To wait. Esperar. Yo espero. Uh, 257.4. Very good. So right force minus left force, 272 minus 14.6 equals, okay, 20A. So when I subtract those, I get 257.4, and that equals 20A. 257.4 divided by 20 is 12.87. So the acceleration of the child is 12.9 meters per second squared. Okay, so that's how that works. We're going to do probably 2 more examples, I think. All right. The next example is going to have a wall. So as opposed to a floor, we are going to have a wall. Now type it into the chat if you know. So for this problem, for both of these problems, we had the y component of the acceleration is 0 and the x component is not equal to 0. Type it into the chat if you know how this problem is going to be different because of the presence of the wall, okay, as opposed to the floor. Let's make this a 20 kilogram box, and there is a 400 Newton force. 400 Newton force pushing upward, and that angle right there is 20 degrees. Okay. And the coefficient of friction, the coefficient of kinetic friction, excellent. So the box is not going to move in the x direction, it's going to slide in the y direction. So probably the box is going to slide upward because 400 newtons is much greater than the weight force. So the box is going to, it's kind of like you're doing something like this. Here's the box, and you're pushing it, and it's sliding up like that. We're going to say that the coefficient of kinetic friction is 0.4. Okay? So let's draw a free body diagram. I'm going to go ahead and get the components of the 400 Newton force. Okay? So 400 sine of 20 is 400 sine of 20 is 137 newtons. And 400 cosine of 20 is 376 newtons. Okay? So, when I draw my free body diagram, this 400 Newton force is equivalent to 376 newtons going upward and 137 newtons going to the right. We have a weight force going downward. The weight force is 200 newtons. Okay? The normal force, in this case, is going to point to the left. And as you can see, the 376 newtons is bigger than 200 newtons. So this box is going to slide up the wall. And consequently, friction is going to point down, because friction is an oppositional force. So if we found that the upward force was smaller than the downward force, the box would slide down, and we would put friction as pointed upward. Okay? So we have friction here. All right? So type it into the chat if you can write an expression for the net force in the x direction. Okay? And while I'm waiting, we can see that because the box is pinned against the wall, it can't move horizontally. It can only move vertically. So that means that the x component of the acceleration is 0. So that's 0. Okay. And by the way, we're also going to do a net force in the y direction equals m times a sub y. So if you want to write if you want to type in an expression for the net force in the y direction, then you could do that as well. I'm waiting for a response. Someone help me. So the net force in the x direction is right forces minus left forces. So you look at the free body diagram, and you look at the forces that are going to the right, and then you subtract the forces that are going to the left. Yahoo! Excuse me. Okay, no one wants to help me. Frowny face. So the rightward force is 137 newtons, and the leftward force is the normal force. So my net force in the x direction is 137 minus F sub n. So that tells me that the normal force is equal to 137 newtons. So this is 137 newtons. Okay? Once you know the normal force, you can then calculate friction. Kinetic friction is mu sub k times normal. All right? So, all right, mu sub k I said is 0.4, so I have 0.4 times 137, like that. 54.8. I'm just going to call it 55 newtons. So that means that friction is 55 newtons. Okay, so now that's going to allow me to write the net force in the y direction. Okay, so the net force in the y direction is up forces minus down forces. Okay, so 376 minus 200 minus 55. Equals, the mass is 20, so that equals 20A. 376 minus 255 is 121 equals 20A. Divide both sides by 20, and I get 6 meters per second squared is the acceleration of this box up the incline. That's an acceleration in the y direction. Okay? So let me recap the steps when you're solving these two-dimensional force problems. Okay? And then we're going to do one last example. So here are the steps. The first step is going to be to draw the free body diagram. Some forces may be variables. Okay, so for example, in this free body diagram, when I started out, I didn't know what the normal force was, and I didn't know what kinetic friction was, so I just left them as variables. Okay. Then what you want to do is you want to use trig to make diagonal forces become vertical and horizontal forces. Okay, so you can see that I took this diagonal force and I used trigonometry to show that it was equivalent to a right force of size 137 and an up force of size 376. Okay. Then what we're going to do is we're going to redraw the free body diagram with all forces up, down, or left, right. Okay, so we redrew the free body diagram with no more diagonal forces. The diagonal forces were replaced with a vertical and a horizontal force. Okay. Then what we do is we do Newton's second law in the x direction, and we do Newton's second law in the y direction. Usually one of those two is going to be 0, okay? And remember, the net force in the x direction is right force minus left forces. The net force in the y direction is up forces minus down forces, okay? And then all you have to do is you just solve the equations. Okay, so I'm just going to type it right in here. Usually 1 is 0. Okay, so those are the steps for solving this kind of problem. We're going to do just one more example, okay, that is a little bit tricky. So what if we had a skier or a snowboarder, take your pick. I like to go skiing. Never done the snowboarding before, so I'm going to pick a skier. a skier is on a frictionless slope, okay, with an angle of 55 degrees. So it's a pretty steep slope, okay? And we want to know, what is the acceleration of the skier down the slope? All right. So this is kind of a little bit tricky at first. So if we draw our free body diagram, we can see that the normal force goes perpendicular to the surface. And the surface is angled, so the normal force goes perpendicular to that. So the normal force goes this way. The weight force, we're just going to say that the skier has a mass of 50 kilograms. Okay? So that means that there's a weight force going down of 500 newtons. Now here's where this gets weird. Okay? I'm going to take my... So the reason that this is tricky is because the skier is accelerating diagonally. They're accelerating up and down, and they're accelerating side to side. So how are we going to fix that? Well, we're just going to rotate our paper. We're going to go like that. So we're just kind of changing our perspective a little bit, okay? Notice how if we change our perspective, the slope is now flat, and it's gravity that is diagonal. Okay, that's a little bit tricky to think about. Okay, so how many degrees did I have to rotate my paper in order to make the ski slope flat? I had to rotate it 55 degrees. So I rotate my paper 55 degrees, okay, and that made the slope flat. So that means that this arrow got rotated by 55 degrees. Okay? So that means that the 500 Newton weight force can be thought of as 500 cosine of 55, so 287 newtons. Okay? And then 500 sine of 55, which is 410 newtons. Okay? So I can redraw my free body diagram. The normal force is going up and down. And then gravity, which is now diagonal in my rotated piece of paper, is equivalent to a 410 Newton force going to the left and a 287 Newton force going to the going downward. Okay, so the net force in the x direction is m times a sub x. All right. There's only one force in the x direction, and that's the 410 newtons. So we have minus 410. It's going to the left, equals m, which is 50, times a. Okay, so 410 divided by 50 is 8.2 meters per second squared. So the acceleration of the skier down the incline is negative 8.2 meters per second squared. All right. So this type of problem is called an inclined plane problem, and we're going to do more of these in our next lesson. So if you don't completely understand this version of the problem yet, that's okay. But you should be able to do these ones. Okay, so that's the end of my lesson for today. I will see you in the Zoom room.